All right, so we're going to continue with graph algorithms. Before the break, before the midterm, we very briefly did some review for graph algorithms, in particular graph representations, as well as a pre-order traversal of trees, so that it would help you on your programming assignment for Huffman coding. As another piece of this review, I just wanted to review the types of graphs that you might see in real life, and of course in your third homework assignment, where the bulk of your programming is going to be doing graph algorithms. So you've got directed versus undirected graphs. Remember that the difference there is if you represent it as an adjacency matrix, then this, if it's directed, this matrix is not necessarily symmetric, right? That the transpose of this matrix, of course, it's not a multigraph, so the diagonal will always be 0, but A goes to C does not necessarily mean that C goes to A. If it's an undirected graph, of course, it would be symmetric. You could actually ignore half of the matrix if you really wanted to, or you could ensure that it's always going to be symmetric. Okay? With an adjacency list, you could store that if the head of your list represents vertex V, and U is in it, right? Then you would interpret this as V is connected to U, but not necessarily that U is connected to V. You would have to look at U's adjacency list in order to get that back edge. Nodes can also be labeled, unlabeled, or weighted. In the previous assignments, we've had you do labeled nodes, but we've made it easy for you by labeling them 0, 1, 2, 3, all the way up to n-1. Edges, likewise, can either be weighted or unweighted. Unweighted edges are basically weighted edges with a uniform weight of 1. And how would you represent each one of these things? Well, again, if it's an adjacency matrix, instead of a 0, 1 matrix, you could put 0 to imply that there is no edge there. And then instead of a 1, you could put the weight of the value instead. Or you could use a library to do all that stuff for you. Okay? And in homework 3, you can. Most of you are using Python, and several of you have used NetworkX. If you want to continue going ahead and using a NetworkX, that's perfectly fine. If you want to roll your own representation, that's also fine. Just as long as you do not use NetworkX and its suite of algorithms in order to solve the problems directly yourself. Right? You can use them to verify that your program code is correct. For example, if you have to write an algorithm to detect whether or not U to V is there's a path from U to V, right? Certainly you can ask NetworkX, is there a path from U to V? Then run your algorithm to find if there's a path from U to V, and do they agree? Do they both say yes? Do they both say no? That's a great way of testing stuff out. In fact, that's how we do it in the grader. We have a known good solution, or we at least cross our fingers most of the time and hope that it's a known good solution. And we've got your solution that we run those against each other. Do they match? Does the expected output match the actual output of your program? Right? So those are the types of graphs. We're going to go ahead and look at the most basic of algorithms first, graph exploration algorithms, or graph traversal algorithms. And the first one that we're going to look at is depth first search, or just DFS for short. Now, you actually already know DFS. You have actually seen it several times already. For example, pre-order and in-order and post-order traversals, they are all DFS but they're all DFS on binary trees, which makes them a lot easier. You don't have to keep track of so much information. If you know that that you've got a tree and that it's oriented and you've got parents, left child, right child, then it becomes really easy. You don't have to keep track of any other additional information other than keeping track of the stack, or implicitly in the recursion, keeping track of that. You've also seen DFS when you did brute force Hamiltonian path problem. That backtracking algorithm that we showed you and that you implemented in your first homework, that was DFS. It was just an inefficient DFS because it explored multiple, if it went down this corridor over here to try to find a solution and it backtracked, well, there's no guarantee that it goes around and finds another way of getting down to that same corridor and repeating every single path multiple times, an exponential number of times. The basic idea here is that you just, in both of these, is that you explore the graph as deep as possible before backtracking. So there's still a sense of backtracking here, but there's not a sense of repetition where you're exploring the same node multiple times or an exponential number of times. There's also less structure because it's not a tree. So you need to keep track of additional information. How do we know that we haven't visited those already? And we're going to keep track of several artifacts, in fact. Okay? So the artifact DFS data. We're going to keep track of several pieces of data here. First of all, we're going to keep track of vertex colors. And I don't have a wide selection of colors over here, so I'm just going to keep track of it using a pencil, which means that I'm going to keep track of it using white, in other words, an uncolored vertex, gray, in other words, I've visited it, and black, that it's done, it's been processed. White will be indicate unvisited, unprocessed vertices. So in particular, before you even start your DFS traversal, everything will be colored white. Okay? Then a gray vertex is a visited but unfinished vertex. Think of it this way. When I go into a vertex initially, right, I'll color it gray because I visited it, and I'll process it, do whatever you want with that. But it has a neighborhood. It has a bunch of neighbors that I also want to explore. So I will go ahead and explore that entire neighborhood as deep as possible, because sometimes backtracking, explore that other neighbor, that neighbor and what it leads to, and then backtracking. Only when I've explored the entire neighborhood does a gray vertex become a black vertex, and it's a finished vertex. We're never going to come back to it because not only have we explored it and we've explored all of its neighbors, we're done with it and everything that it's connected to, so we need to keep backtracking. Right? We're also going to keep track of some other data here. We're going to keep track of discovery times, and we're going to keep track of finish time. And these will help us later on when we want to do what's called topological ordering. Okay? So a discovery time is simply just a timestamp. Both of these, we're just going to keep a counter. We'll start it at 1 and increment every time a color changes. Okay? And then we're going to stamp that vertex that we just changed its color from white to gray and then to black. We're going to stamp it with that timestamp, and we're going to see what that gives us. Okay? So that's our DFS data that we're going to keep track of here. I've already pre-drawn a graph here, 9 vertices, and it's an undirected graph. So we're going to keep track of all that metadata, and I'm simply going to use my pencil here. I'll use slashy lines to indicate gray, and then if I do slashy lines in both directions, that'll indicate black. Okay? Now there are lots of criteria that you can use to actually traverse your graph. We call that our next vertex choice. So you've got a lot of choices, right? You could visit the next vertex with the edge with the least weight, right? So you could visit the least weight edge next. Or, if you wanted to be greedy or something about that, you could visit the greatest weighted edge next. If it was unweighted or they all had uniform weights of 1, well, okay, you can randomly choose, right? It could be random, right? Or you could choose lexicographically. If your vertices were labeled 0, 1, 2, 3, 4, 5, 6, well then you could go to the next least weighted, least numbered vertex. And that's what we'll do. Here's our graph again. And what we're going to do is we're going to use, because it's unweighted, we're going to use the lexicographic next one to go to. Now with that in mind, where should we start? We could start at an arbitrary vertex if you wanted to. But if we want to be consistent about it and go with lexicographic next, well, which one's the lexicographic first? A. Okay. So we'll start at A here. And I'm going to keep track of several things over here, including A. What do we call that? Stack. Why do we want to stack? Do you remember pre-order traversal? Do you remember the brute force Hamiltonian path exploration algorithm? Both with the pre-order traversal, you could do that recursively if you want to, just like you could do in-order traversal recursively if you want to. But basically, you're using the call stack as a stack. And so we can use an in-memory stack instead, just like we do with pre-order traversal, or we could do this recursively and use the call stack to keep track of our breadcrumbs. Remember breadcrumbs? You need to, Hansel and Gretel go into the forest, they leave breadcrumbs behind them so that they know how to backtrack and get back home. We're going to do the same thing. We're going to explore deep into this graph because it's depth first search. But we need to know where we came from so that we can backtrack and find our way home and explore other areas of the graph. Okay? So there's my stack. I'm going to go ahead and start again at A. We're going to push A, right? And we're going to color it gray. Right, that's my representation for coloring it gray. Everything here is initially white because it's unvisited. If we start our visitation at A, then we're going to push it into this stack to keep track of that's where we are, and when we go and leave A, that's where we came from. Okay? And I'm also going to timestamp it with 1. That's our discovery timestamp. Okay? I'm going to keep a track of a counter, 1, 2, 3, 4, and every time I change color or visit a new vertex or finish a vertex, I'm going to timestamp it with that current counter. I'm going to separate the discovery time and the finishing time with a colon here. Okay? I'm at A. Now look at its neighborhood. Its neighborhood is all of the vertices that are connected directly to it. B, C, and E. And they're all white vertices. In other words, they're all unvisited vertices. Which one should we go to next if we're going to be lexicographic about it? B. So I will push B, color it gray, and now this is my current vertex. I'll keep my finger on the current vertex all times. We just colored it gray, so we increment our counter 2, and that's our discovery time for B. Okay? So vertex A, B, discovery, and finish. All right. We're also going to use these to generate several more artifacts, okay, that will help us later on. So now I'm at B. I look at its neighborhood. What's its neighborhood? Both A and C. But what can you tell me about A, and what can you tell me about C? What about A? Look, it's gray, so we've visited it already. Do we want to go back to it? Not yet, because we're depth first search. We want to continue exploring the unknown, the things that we've not seen yet. So that's not a candidate. We only look at the white colored vertices in the neighborhood. And we go to C next. We push that, and we increment our counter, A, B, C, 1, 2, 3, so far. Okay? And there's my current vertex. I look at its neighborhood, which is actually quite rather large, right? But A and B are gray vertices, so those are not in contention. Those are not things that we want to go to next. I look at E, F, and I. If we're going to go in lexicographic order, which one do we go to next? E.
I'll leave room here for D. And we discover it at timestamp 4. And color it gray. Okay? And we push it onto the stack. At this point, look at our stack. Our stack represents the path that we've followed so far. We went from A to B to C to E. A to B to C to E. If we were to reverse this, it would take us all the way back to the beginning. Okay? All right. So we're at E. We look at its large neighborhood here. And A and C are gray, so we don't want to go to those. We instead look at D, G, and H. So we go to D next. It's discovered at timestamp 5, and it's colored gray. Now, here's where something different happens. I'm at D. I look at its neighborhood. The only thing in its neighborhood is E, which is gray. We've reached a dead end. If you want to look at this as a maze, we've reached a dead end, so what do we need to do if we reach a dead end? We need to backtrack. We need to go back to where we came from. Before we go back to where we came from, though, we want to finish this off. We color it black and timestamp it with a finishing timestamp. So that when I get back to E here, I see its neighborhood, A and C. Well, those are still gray because I've visited them before, but they're not done yet. But also I see D, well, that's black, it's finished. I definitely don't want to go there because I know that that led to a dead end. Okay? I look at the rest of the neighborhood, G and H, E, F, G, H, I. So where do I go next? What lexicographic next would be G, and it's discovered at timestamp 7. And we color it gray. I look at its neighborhood, and there's a gray vertex and a white vertex, so I go to H next. Stamp it, and go like that. I look at its neighborhood, and I see, oh, okay, I is the only thing in its neighborhood that is unvisited, indicated by the color white here. And so I go with 9, timestamp it, and now I'm at I. Oh, by the way, what did I've been neglecting my stack here. What happened to the stack? Let's reverse here. When I was at D, right, I then backtrack. So what I went from A to B to C to E to D. At this point, I backtrack. So what do I do with D? I pop it, right? And now I'm at E. Then I went to G, H, and I. So my stack looks like G, H, and I. Right? Now look at that long path. The path that I followed was A, B, C, E, G, H, I. Right? That's how I got all the way to this vertex right here. And I'm keeping track of that using this stack here. At this point, though, I look at the neighborhood, and C and H, they're both gray. So what do? I color this black to indicate that it's done. I timestamp it, 10, and I pop it off the stack. Popping it off the stack basically changes my current vertex. If my current vertex is I, and I pop this off the stack, the thing at the top of the stack, if I peek at the stack, that's my current vertex. So that's how I'm keeping track of my backtracking. Now I'm at I. I look at the neighborhood, only gray and black vertices. So what do? I'm done with it. 11. Color it black and backtrack by popping it off the stack. Now I'm at G as a current vertex. 12, colored black and popped it off. Now I'm at E. I look at the neighborhood, 3 black vertices and 2 gray vertices. So I again increment my counter, color it black, and pop it off the top of the stack here to return to C. 13. There we go. Well, now look at this neighborhood. There are gray vertices, there are black vertices, but guess what? Because we've backtracked all the way from I here, we backtrack, now we'll finally discover F. We'll discover it at timestamp, where are we? 14. Color it gray, it gets pushed on the stack. So 14, discovery time. Except that we've reached another dead end. So we end up coloring it black, labeling it 15 for discovery time, backtracking, now we're at C. right? And we'll end up backtracking all the way here. So it'll be 16, 17, and 18. Right? So 16, 17, and 18. And pop, pop, pop. How do we know when we're done? We've gotten all the way back to the beginning. Everything has been colored black. How do we know that without checking all the colors? Well, empty stack, exactly. And you'll remember that from a pre-order traversal. While the stack is not empty, continue processing. Right? And that's exactly what we're going to do now. We're going to codify this as a full algorithm here. Okay. A few other things to note here. Right? The discovery time, it was not dependent on the labels. It's dependent on the topology of the graph, the shape of the graph, and its connectivity. But what about the finishing timestamp here, 18? What does that correspond to? How many vertices were in the graph? 9. So we're going to run from 1 up to n in general for all timestamps. Okay? And what can you say about A here? Its discovery timestamp was 1. Well, if that's where you start, then its finishing timestamp is always 18? Okay, maybe. Let's look at it from the perspective of a different graph. Here, maybe, maybe not, right? What if I had another edge over here that was vertex, that was isolated? A, B, C, D, E, F, G, H, I, J, right? And it was connected to it, I, J, K, and L, right? You could have a disconnected graph. That is entirely possible. Right? In fact, one of the algorithms that you can use DFS for is to discover, is this a connected graph or is it a disconnected graph? Right? And that is that's a very common operation that you might want to do. Right? But another way that you can do DFS is that will lead to even more different results is to do it on a directed graph. Right? With a directed graph, can I go from C to A? No, so that would not even be in the neighborhood. This is the same graph, same edges, same vertices, but it's oriented. Right? You don't necessarily have those back edges. So let's do it as an example one more time here, and let's see how different it is. All right? Same artifacts, same criteria, and it'll probably lead to a different discovery time. Different artifacts that are like discovery times and stuff like that. All right? Let's go ahead and keep track of everything in a stack. That's a thin stack. Doesn't need to be that big anyway. All right. So vertex, discovery, and finish. We'll go ahead and start at A, just like we did last time. But the neighborhood here is, I don't know, it looks a little different at least, is going to be, we're going to discover it at timestamp 1, color it gray, look at its neighborhood, and of course push it here. Both B and C are white, so we can go to them because the edges are oriented in this direction. So we'll go ahead and go to B because it is the lexicographic least. Right? Timestamp it as 2. And now we're at B, because that's at the top of my stack. And we look at its neighborhood. Well, its neighborhood is only one vertex, which is C. Right? And we go to that, and we color it gray, timestamp it at 3. There we go. And now we're at C. Look at its neighborhood, though. Not all. It's much different than the previous graph. All of these are incoming edges. Those are not part of its neighborhood because we cannot go to those vertices, those vertices directly. The only thing in its neighborhood is what? E. And so we are forced to go there. Oops. I'll go ahead and leave D here. I will go in order. Right? And so now we color it gray. It's at the top of our stack. Look at its neighborhood, D, G, and H. And they're all white vertices, undiscovered. So we'll go ahead and go to D next. And its timestamp is 5 as a discovery. Right. At which point, we've, just similar to the previous example, we've reached a dead end. And so we need to start backtracking. And it'll have a finishing timestamp of 6. We're at E here. And so we'll end up going to G. And that's a timestamp of 7. Color it gray. And by the way, we popped D off the stack. And now we've got G on the stack. Don't ignore my stack here. All right, we're at we're at G. I go then, the only thing that I can go to is H. Color it gray. It's discovered at 8. 7, 8. And then I look at its neighborhood. Well, E is not in its neighborhood because this edge is coming in as an incoming edge. I is. And so I go to it and I discover it at 9. And I push it onto the stack. There we go. Now I look at its neighborhood. Its neighborhood is C, but C is gray. Another thing that you can notice here is if you ever see a gray vertex in the neighborhood, then that you know that it's somewhere in the stack already. Right? So I end up backtracking. 10. Color it finished, black. Backtrack. 11 for H. And then backtrack, 12 for G. Color it black. And I've popped all of these things off the top of the stack. I'm now at E. Everything has been visited and processed and is done in its neighborhood. So I backtrack, right, and pop that off the top. 13 for E. Backtrack. Now, before I could go to F, but can I go to F from C? Nope, because it's an incoming edge. So I just continue backtracking. C is popped off the top, colored black, and where am I, 14? A, B, C, D, E, F, G, E, F? Uh-oh. What about those? Oops, oops. There we go. Backtrack. B gets popped off the top, and that's a finishing timestamp of 15, and the finishing timestamp of 16 when I'm done. With an undirected graph, am I done now? Have I explored this graph entirely? No. I need to start over. Just like an empty stack may not necessarily say that you're done if you've got a disconnected undirected graph. So we restart our searching at any white vertex. If there are several white vertices, then again we could break our ties by looking at lexicographic or weights or something like that. But there's only one in this case. And so I end up discovering it at timestamp 17. And then of course, gray, this is black, so I push it, I pop it, and it's done. And now I'm done. So what's another criteria that we could use if the emptiness or the fullness of the stack is not a good criteria for stopping our search? Over here, we knew where we were done when this is empty because it was connected. And the last timestamp was 18, twice over 9. Over here, it's 16. What do I know? I've got unvisited vertices. So that's another criteria that you can use. Okay? All right. So that's the basic idea. Let's go ahead and operationalize this, realize this with an actual algorithm. Now, in the notes, or in the book, or whatever you want to call this, it's a little bit more than notes, a little bit less than a book. In the notes, I do have a recursive version. If you really like recursion, go ahead and go with it. I'm going to show you the stack-based version, right? Because that's the one I just simulated over here. So here's our algorithm. It's a stack-based DFS, depth first search. Our input is simply going to be an undirected graph. An undirected or directed, I'll go ahead and leave that blank because it'll work either way. A graph, G equals V comma E. All right? And our output, well, it really depends on what you're trying to do, but this is going to be a very generic. Our output is simply going to be a DFS traversal. So DFS traversal. Right? It all depends on what your nodes represent. right? In a binary search tree, your nodes represent keys. Those keys then represent, objects, that you're searching for a particular object. You're searching for a node that represents a code word or something like that. And so what are you trying to do? Well, this is so generic, so abstract, that I don't know what you're trying to do. It's just a graph, so we'll output each vertex in some order, right? We'll output them in discovery time. We'll output them in finish time. It's all up to you on it's all up to you on what you're actually doing with these nodes, what these nodes represent, and then you process that, each one of those things, right? You could also say that I'll output all the artifacts. I'll output a set of all the discovery times, all the finish times, whether or not, all the connectivity things, whatever, right? It's so generic. This algorithm that I'm showing you is so generic it can be applied to many, many different problems, as we'll see. So I'm going to keep it generic. And if you need to, you can come back in and insert another line to actually get what you want. All right? So what we're going to do is we're going to start with an initialization. For each vertex, v in v, what we're going to do is we're going to color v white. This is an initialization. We want to make sure that we have not missed anything, so we need to make sure that everything is undiscovered at this point. We're going to set up, that's not all for our initialization. Our count will be 1. That's where we're starting. And we'll create an empty stack. So this is our initialization as well, right? We're just setting it up. Now, we need to get started somewhere. So an arbitrary vertex or whatever, we'll say that we'll push the start vertex v onto S. Now, when we do that, when we did that over here, we also did a couple of other things, right? When I pushed A onto the stack, we marked it. We also colored it gray so that we could say that, well, I visited it, right? Because that you have to start somewhere. It's like you're putting your foot on that vertex. So we'll push the start vertex on there. We'll color it. We'll stamp v with count. This is the discovery time. All right. And we'll color v gray. I've got AY. All right. So this is the start of the search. There we go. All right. You could think of all of that as being initialization, but I like to think that this is initialization because you're setting up all your other variables, and then this is actually starting the searching phase. If you actually need to process what's stored at the node or what the node represents, well, you'd also need to do that here, right? Process whatever whatever data v is holding at this point, right? And you'd want to handle that separately outside of your main loop. While S is not empty, we will do the following. First of all, we need to increment our counter because we're about to discover a new vertex. So I'll go ahead and go with count plus plus. What I need to do is I need to look at where am I, right? I need to look at the top of the stack. Now, do you remember what operation there is that you can look at the top of the stack but not get the element and remove the thing at the top of the stack? What was that called? You just want to take a peek, right? Peek. Remember, the stack, the thing on the top of the stack tells you where your current node is. So X is our current node. That's where I'm standing right now. I didn't take it off the stack. I just ensured that I'm looking at the top of the stack and that's where I am. Okay? So that's you don't have to keep track of a different variable that you update on every iteration of this loop. Okay? What we're going to do is we're going to look at the neighborhood next white vertex in the neighborhood of x. Okay? So x is the current vertex. Y is where we're going to go next, is the next. I'm only restricting my attention to the neighborhood of x, and I'm only looking at the white vertices in that neighborhood because I want to go to an undiscovered vertex. Okay? Now, I've got some choices to make here. First of all, what happens when there's nothing in the neighborhood? For example, when we got all the way over here, remember when it was, this is gray and this discovered time was 9. We looked around the neighborhood and saw, oh, this is a gray vertex, this is a gray vertex. There's nothing in the neighborhood that I can go to. Right? What did we do in that case? We started backtracking. So if y is phi or nil or whatever you want, in other words, there's no white undiscovered vertex in the neighborhood, then we've got to backtrack, right? What are we going to do to backtrack? What did we do over here in the example? When I started backtracking with this, at I, what did I do? I colored it black. I time-stamped it with a finishing timestamp. And then what did I do to the stack? What was at the top of the stack? I was at the top of the stack here, right? You can still see it faintly. What do I do to get rid of it? I pop it off. Right? So I will go s.pop, right? Remove, backtrack. Right? Then I will process x. Note that I'm not capturing the value when I pop it off because I've already got it up here as x. I peeked at it. Well, you can go ahead and pop it off and restore x here if you really want to, but you don't have to. Color x black because it's done. Stamp x with count. And note that I've already incremented it up here, so I don't need to worry about incrementing it down here. The next iteration of this while loop will take care of incrementing it to the next one for me. With count, this is going to be the finish stamp. Okay? There's no white undiscovered vertex, so I need to start backtracking. If I backtrack, then up here, I'm going to look at the next thing. I've already popped this off, so if I went A, B, C, and those are A, B, C are in my stack, then I pop off C, well, then next time I peek, it's going to be at B. So I'm backtracking back to B, backtracking back to A. Right? Dot, dot, dot. Unfortunately, I've run out of room, so I will go ahead and go to the next page here. Else, it is a rather long one the way that I've written it, but that's fine. Also, I need to go to it. Remember, Y represents the next vertex that you want to go to. So what do you do to go to that vertex? What did we do to go to V here? We pushed it onto the stack, we stamped it with a discovery time, and we colored it gray. We do the exact same thing down here. We will s.push the current vertex x. We will color x gray. And then we will stamp x with count. Now, if you want to this is going to be a discovery. Note that if else, you're still stamping it, you're still coloring it, but you're doing it differently. Here you're stamping the finish time. Here you're stamping the discovery time. So those are two different operations if you want to keep track of all of those artifacts. And that's the end of the while loop. All right. This is a stack-based DFS traversal. Be careful, though. This is only one iteration. You may have to start over. You may have to start over, right, in a main loop. Okay? So was that your question? Or no, what's your question? pushing Y, and you're coloring Y, and you're stamping Y. X is already stamped. X is already on the stack because that's where you peaked, right? Sorry. Oh, it is correct on my notes, so don't worry about the notes. They are correct. Okay? It was my transcription of the notes that was not. So you may have to start over because, especially if it's an undirected graph and it's disconnected somehow, well, then this entire subgraph over here might still be all white vertices because you can't get to it from where you started. Likewise, with a directed graph, you may definitely have to start over if you've got what are called sinks or sources. Sources are things that don't have any incoming edges. There's no way to get to them, but you can leave them if you want to. And sinks are just the opposite. They only have incoming edges, no outgoing edges. So you can come into them, but you can never leave them. Okay? For example, here. This was a source because there's only outgoing edges. This was a sink. This is also a source, so you can have multiple sources, multiple sinks. And this, of course, is neither, because you can get into it and you can leave it if you really want to. All right? And so you can label them. I think that's it. Yep. Okay. That is a stack-based DFS. If you really want the recursive version, by all means, go ahead and read the notes, and you can check it out. But what I want to do is I want to go back and I want to redraw this. Okay. Let's look at this graph right here. Let's look at the undirected version first. Okay. So this is the graph. I want to reorient this to produce what's called a DFS tree. Right? Let me go ahead and write down the DFS tree. Uh-oh. Whoa. Never had that happen before. The entire thing popped off. Okay. DFS tree. So a DFS tree is where you can actually label the edges. You can label edges as a result of DFS. There are going to be tree edges. Right, we're building a DFS tree. There are going to be tree edges. These are the edges directly traversed with DFS. You can also have forward edges and back edges and what are called cross edges. Okay. Forward edges and back edges, well, with an undirected graph, they're the same thing because there's no orientation. But a forward edge connects an ancestor in the DFS tree to a descendant. I'll use bad handwriting there because I don't know how to spell it. And a back edge connects a descendant to an ancestor. And cross edges, well, they connect cousins, you could say. Right? Distant cousins, second cousins removed, I don't know all those terms. Or siblings, right? Or siblings, possibly, right? Basically, if it doesn't fall into one of these three categories, then it's going to be a cross edge. If you don't have a direct ancestor-descendant relationship, you know, you've got a cousin relationship of some sort, then that's going to be a cross edge. So to visualize what I'm talking about here, let's go ahead and go back to this one over here. Okay? So let's retrace our steps. Remember DFS. I started at A. Where did I go from there? I'm going to go ahead and use red here. Where did I directly go in my DFS search? I went from A to B. Right? I went from B to C. Where did I go next? E. Right? In fact, do you really even need to keep track of this stuff? I've crossed them all out, right? Why did you know to go over here other than your good memory? 3? Yeah, you have 14 or 4. Which one did I go to next? 4, the discovery time. Then I went to 5, then I backtracked. Then I went to 7, 8, 9, backtrack. Then I went over here, right? Those are my tree edges. What I'm going to do is I'm going to redraw this as a tree to show you that it in fact is a DFS tree, right? So here's A. Then we went to B. Then we went to C. Then we went to E. Then we went to D, at which point we reached a dead end, and we had to backtrack. So we had backtrack. Where did we go after that? We went to G. Then we went to H. Then we went to I. Then we backtracked, and then we went to A, B, C, D, E, F. I think that is F, off of C. There. There's our DFS tree. Right? Those are the direct routes that we took in DFS. Now this is in contrast to the Hamiltonian path problem I gave you the brute force solution of this. That you would end up visiting a vertex multiple times, right? And in that case, that wouldn't produce a DFS tree. I mean, it would kind of produce a DFS tree, but we had multiples, right? The vertex B could appear here and here and here and here. It could appear 50 times, depending on how many paths it was involved in. But here, every vertex appears exactly once. And if every vertex appears exactly once, and we're guaranteed that we never cycle back onto anything, then we've got ourselves a tree here. And it's a tree of size n, where n is the number of original vertices. So instead of that exponentially sized tree that we have with Hamiltonian path brute force, that computation tree, we've got a nice linear sized tree here. Now those aren't the oldie edges, right? What are some other edges that we have here? A to C. What does that look like? I'll go ahead and draw it. What kind of an edge is that? Is that a forward edge, back edge, or a cross edge? Well, it connects an ancestor to a descendant, but it's undirected. So it also connects a descendant to an ancestor. So with an undirected graph, these are the same thing, right? So we'll call it a forward edge. Forward / back edge. All right? Oops. So that takes care of that. What about A to, and I think this is E, A to E? What kind of an edge is that? Also a forward or back edge. What about this one? What was this? I to C? C to I? Darn it. That's also A. That is a forward edge. Why? This is an ancestor of I, and I is a descendant of C, so this is a forward or back edge. So no cross edges here. Okay. I wonder why. All right, we'll come back to it. Could there be a cross edge right here, D to G? What if that were here? Let's go back over here. D to G. What if that were here, right here instead? What would have happened with DFS? Remember we went A, B, C, E, and then D. Originally it was a dead end and we had to backtrack. If that edge were here, would that be a dead end? Nope. So we would get a different DFS traversal, a different tree. Right? Think on that for a while. But I want to look at the same thing, but with a directed graph. So here's our directed graph. And Unfortunately, I did mean to draw it completely different, but I think we ended up with the same thing. We went from A to B. Come on. We went from A to B, then we went from B to C, then we went over here, 4, 5, backtracked, 7, 8, 9, then we backtracked, and then we started over here again, right? So this is a tree edge, but now it's no longer a DFS tree, is it? It's a DFS what? A to B, we went then to C, then we went to E, we got stuck in D, backtracked, we went to G, and I am orienting the edges here in this DFS tree, right? And then from there we went to H, we went to I, and then over here, remember, we had to start over at A, B, C, D, F, right? There. That's not a DFS tree. What is that? 2 trees. What do you call 2 trees? At least in computer science. It's a forest, right? Now, in real life, 2 trees don't make a forest. 5 trees don't make a forest. And that's a very good philosophical question. How many trees does it take to make a forest, right? It's just you can look at a forest and say, yeah, that's a forest. You can look at a couple of trees sitting on the side of roads. Nah, that's not a forest, right? So where is the cutoff in between? When does a forest become not a forest, right? How many trees do you have to cut down and then to make it a forest? So what about the rest of these? Remember that I goes to C, I goes to C, and that was oriented that way. So I goes to C. What kind of an edge is that? It goes from an ancestor to, a descendant to an ancestor, so this is a back edge. All of these are tree edges. What about another one? What about A to C? That is a forward edge. What about, is there another one? E to H. There we go. That's a forward edge. What about F to C? I shouldn't have colored it red, by the way. F to C. Is F an ancestor of C? Or is C an ancestor of F? No. Was this involved directly in a tree, in the DFS tree? No. So that only leaves one possibility. What? It's a cross edge. Right? So we can have cross edges, back edges, and forward edges in our DFS forest. Right? This is the DFS tree for undirected. Okay? So those are yep. You can also, I didn't have one here, but you can have cross edges in the same component. For example, if I had D to G, remember my argument over here that this can't happen? Because if it happened, you would have gone to G. But it's okay if it's oriented because that is a dead end still. You can't get out of that and go over to G because it's oriented this way. So this would be a cross edge in the same component in a DFS forest. And that would correspond G to D if I had this thing right here, right? If we had that edge right there instead. So you can tell a lot of things about a graph depending on whether or not it has these components, right? So let's go ahead and enumerate what we've already witnessed here, what we've already observed. For undirected graphs, we know that forward and back edges are the same in the DFS. Now again, I am calling it tree, but it could be a forest, right? Even with an undirected case, if you've got disconnected graphs, ABC over here, XYZ over here, but there are no edges between those two components, we call those components, then you can also have a DFS forest, and you might need to start over again. For undirected graphs, are cross edges possible? Cross edges are not possible. Because with an undirected graph, if you have a cross edge, then that means that you have a way of getting out of that vertex, and therefore it would be in the DFS tree to begin with. Okay? But you can have forward edges and back edges. For undirected graphs, why is this important? Well, of course, cross edges, we don't have those. But if you have a forward edge or a back edge, what do you know about the graph? Let's go back to this one, this example over here. What do you know about this graph? In particular, what do you know about C and I? You can go to C and I, and not only that, you can go I, H, G, E, C. So what is this thing right here? A cycle. Right? So forward or back edges imply a cycle exists. So, given a graph G, determine whether or not it is a tree. In other words, determine whether or not it has a cycle. Right? How do you do it? Run DFS. If you ever have a situation where you've got a forward edge or a back edge, then you've got a cycle, and you can report, no, it's not a tree, or yes, it is a tree, or forest. For directed graphs, is that true for directed graphs? Does a forward edge imply a cycle? Is there a cycle here between A, B, and C? Is that a cycle? Nope. Cycles in directed graphs have to be directed cycles. So forward edges don't imply that. But wait, what about back edges? C to E to G, H, I, and then you can go back to C. Well, what's that? It's a cycle, right? So back edges imply a cycle, right? All four are possible. And cross edges may connect vertices in the same components, same or different components. All right. How do you tell? And cross edges may or may not imply a cycle. Right? You have to be real careful there. There might be a cycle involving it, and there might not be. It really depends. So you already see a contrast here between undirected graphs and directed graphs. Right? Directed graphs, one way of looking at it is that they've got a lot more structure, because you have a lot less options coming out of this algorithm. There are no cross edges. Forward edges and back edges are the same thing. You only need to have one way of detecting a cycle. Down here, there are lots more possibilities. All four are possible. Cross edges may or may not go between components. Cross edges may or may not imply a cycle. There's a lot less structure here. Think back all the way to how we represent these graphs. Which one has more structure? Which one has less structure for undirected graphs? Think about an adjacency matrix here. An undirected graph, what can you tell me about this matrix right here? It's symmetric. Symmetry is a property. Symmetry is structure. Right? More structure, less options, easier to reason about. But with a directed graph, it doesn't have symmetry. Less structure, less easy to reason about, right? And this is, in fact, bears out in theory. Up until, I believe, 15 years ago, the connectivity problem, this is complete theory, by the way, like theoretical, like mathematical stuff that we don't want to even get into here, that solving the connectivity problem on undirected graphs was a lot easier, right? It was shown to be in what's called a complexity class called log space. DFS, of course, on either one of those graphs, that's going to be polynomial time. Right? We'll talk about the analysis here in a second. But from a theoretical point of view, there's an even stronger class called the log space. In other words, can you do it without a stack? That's basically what we're asking. Can you do DFS without a stack? And the answer turned out to be about 15, 20 years ago, the answer turned out to be yes, you can. The answer of yes, you can or no, you can't for undirected graphs still remains open. Right? My PhD thesis made a small amount of progress towards that along with my collaborators in saying that for planar directed graphs, you can solve the connectivity problem in unambiguous log space, which is an even more theoretical complexity class. But neither here nor there. Right? The connection, not to connect it to my PhD thesis or anything like that, but the connection is back to data structures. Why do we like data structures? Because they provide structure. That structure can be exploited for efficient algorithms. If we've got more structure, all the better. More efficient, easier to reason about. Less structure, less efficient, less easy to reason about. Right? All right, well, what about some analysis here? So, how many times is each node processed? Each node is processed at most once. Right? Another way of looking at this, depending on how you want to look at it, you could say that processing is your elementary operation, and that's fine too. You could say that coloring a vertex is your elementary operation. You could say that stamping a vertex is your elementary operation. All right? You could say that, that putting it into the stack is your elementary operation. Each node is pushed exactly once and popped how many times? Exactly once. Right? Each node is colored. Well, I guess if you count the initialization, exactly 3 times. It goes from white to gray to black. Right? Each node is stamped exactly twice. 2 times. Right? What does all of this suggest? It doesn't matter what you look at as far as your elementary operation goes, right? You're still all looking at what kind of an algorithm? An order n algorithm, right? That this is going to be linear with respect to the number of nodes. That's one way of looking at it. Another way of looking at it, let's go back to the pseudocode over here, if I can find it. What other operations did we do? You remember? Where is it? Okay, must be over here in this file. Yep, here we go. Here it is. What other operations did we do? Let's look over here. The next white vertex in the neighborhood. Right? We have to make a
judgment, a decision on where we're going to go to next, right? We've already seen what happens when you try to examine the neighborhood of a vertex, right? It all depends on how you represent it. If I want to get the neighborhood of a vertex, and it's represented as an adjacency matrix here, what is that going to do? What is that going to look like? What do I have to do to get the neighborhood and choose my next vertex if I'm at A? Oh, it's not connected to A. Not connected to B. Oh, it is connected to C. Maybe that's next. Oh, it is connected to D. Maybe that's next. I have to look at the entire row, right? So a caveat to this would be, however, right, choosing the next vertex may be an order n operation. Even with an adjacency list, if I gave you the list of your current vertex, you'd still have to go through and say, oh, this is white, this is gray, nope, I can't go to that one. This is white, this is black, I can't go to that one because it's already done. And you would get a subset of those neighbors. Then you would make a decision on where to go to next. Right? So even with an array with an adjacency list, you might have to traverse that entire list. Right? Order n or order m operation. Because if you're doing an adjacency list, then you don't have to go over the entire row like you do with an adjacency matrix. All you have to do is go over each element, and that represents the number of edges instead. Right? So you could look at this as overall, it could be order n plus m. That really depends on how you represent your graphs. Does this matter all that much? It's either order n plus n squared, which is going to be order n squared, right? Or you can look at this as order m, because this lower order term doesn't really matter, right? It doesn't matter, right? This is n squared, this is m. It's always going to be linear with respect to the input size. If you've got an n by n matrix, that's linear with respect to that representation. If you've got an array, an adjacency list, that's linear with respect to that representation. Right? Because the number of lists that you have and the number of elements in each list that you have, that corresponds to the number of edges. Right? So at the end of the day, it's going to be a linear algorithm no matter what. And that also really doesn't matter, because probably the most expensive thing you can do with a graph is actually process the nodes. Because presumably, you're pulling out data from that node and doing some number crunching on it. And that's where the real work is. Right? So if you're processing nodes, then it's done at most order n times. It all depends on how you look at it. But at the end of the day, it doesn't matter how you look at it. It's still going to be linear with respect to the input size, regardless of the representation. Okay? All right. Any questions so far? All right, then, just as a preview of tomorrow, let's look at another alternative, breadth first search. So, breadth first search has you not going, you've got a maze, right? A maze where you can go as deep as you want to in the maze, and it's okay because you've left breadcrumbs behind you. You can get back to where you came from. An alternative would be to explore, cautiously, right? Explore all the corridors within, 10 steps or 10 feet or something. Now explore all the corridors within 20 feet. Now explore all the corridors within 30 feet, right? It's kind of like a radial search pattern. If you were searching for a missing person, what would you do? You would establish a radius, and you would search everything inside that radius. Then if you found them, you're done. Otherwise, if you didn't find them, then you increase the size of your radius. Right? Why do you do this in, like, say, a missing persons kind of scenario?
Well, you assume that they didn't go far, and so you search for the closer areas first. But also, what happens as you expand your search radius here? What happens to the area under consideration? How does it go up? What is the area of a circle? Pi r squared. So as r tends towards infinity, what happens to the area here? A grows, not exponentially, of course, but it grows quadratically. And we've seen that that's terrible for algorithms. If you double the size, then you quadruple the area. Right? And that's why when you order a pizza, do the math. Do you get the 12-inch or the 14-inch? Right? And what's the actual difference in the surface area of your pizza? And does that correspond to the value, the extra money that you're paying for it, right? And if not, then just get 2 mediums. All right. So with respect to a graph, you're not searching. Of course, a graph is not necessarily just radial like this, but the basic idea is that you search all nodes a distance 1 from the start node. Then distance 2, then 3, then 4, ... When do you stop? What's the maximum distance node in a graph with n vertices? 4 vertices. What's the maximum path that you could have? 1, 2, 3. So n minus 1. Right? Not only that, but I love the contrast of DFS and BFS. I also cover this in 156 when you do with BFS, the pre-order, in-order, post-order. Those are all variations on DFS for trees. There's another way to search trees by searching at the top, down to the bottom in a left-to-right manner. Right? So you can start at the top, then visit the left child, then the other sibling at the same depth. You're doing everything at distance 1. Then you do everything at distance 2, left to right. And everything at distance 3, left to right. And the contrast between these two is perfectly exemplified by a smart data structure. Instead of a stack, we're going to use a queue. Right? In fact, I like covering it in 156 because when I present the pseudocode for pre-order traversal and BFS, the lines are virtually identical. Put stuff in, take stuff out. The only difference is the data structure that you use. Instead of a stack, you use a queue. And when you do that, you get FIFO order, first in, first out, instead of LIFO order. And that small change completely changes how you're searching the graph or searching the tree. Right? And that goes to the whole point of 156, hopefully. If you took it from me, great. If not, then it's a quote by Eric S. Raymond. It says, smart data structures and dumb code are a lot better than the other way around. Queues and stacks are simple data structures. They're a little bit smart. Right? There are smarter data structures. But that's the power of data structures in your algorithms. If you take one data structure and you put it into an algorithm, then it gives you one behavior and with different structures and different properties. You take the same exact algorithm and you put in a different data structure, and it gives you completely different properties and different behavior. Right? But it still gives you something useful, maybe. Right? Use a heap, and you've got a sorting algorithm because you're putting stuff in, you're taking stuff out. You're exploiting the smartness of the data structure. So that you can have dumb code, put stuff in, take stuff out. And that's what Eric S. Raymond is getting at, that smart data structures and dumb code, pseudocode or actual code, doesn't matter, are a lot better than the other way around. Right? And it also goes to development time from a software engineering aspect. Right? Don't reinvent the wheel. Understand what data structures there are, the advantage that each one provides, and the appropriate application of those data structures can solve your problem.